So friends, thank you for turning the quizzes in. Make sure that you guys turn in a quiz for your group of 2. I think maybe some groups had 3 just to get the last in-class quiz points in. Some of you need one more quiz. Very few of you. Most of you guys are done with your quizzes that you need. Don't forget, speaking of that, you still have up till, I guess, Thursday to turn in your exam corrections if you want to do that. Very few of you have done it. And the quiz correction, if you think it's worthwhile, if it's worth your effort. Now, some of you might figure out that at this point in the game, it's not worth your effort to turn the quiz correction in. If your lowest quiz grade is like a 7, and you're getting 3 points back, that's probably not going to affect your grade all that much at this point. But of course, it might. I've seen 2 and 3 points actually affect the grade, so you guys make that decision on your own. It's there if you want it. It's there if you want it. Okay, so I used to have students draw their histograms on the board. I think on the quiz it actually says that. Come grab a marker, I have the colors waiting for you. And then, I don't know, for some reason as you were sitting down doing your work, I'm like, what the hell, let's put it in Excel and see what it looks like. Now this might be confusing, and that's okay. What I can do is I can just turn certain groups off, we can put them back up. What I want you to do is I want you to look at each of the groups' sampling distributions. What you guys just created was what's called a sampling distribution, which means you drew a sample from a population and you graphed the results of your samples. So here's the red sampling distribution. The blue one is tucked in behind red. Let me delete red for a second so you can see it. There's the blue one right there, blue sampling distribution. There's the yellow sampling distribution. There's the green one, and there's the orange one. Now, what do you notice about all of these sampling distributions?
They're all bell-shaped.
They're all bell-shaped. What the hell?
Even red?
Even if I could break it down more, which I can't because of the data, it's arguably more bell-shaped than it is not bell-shaped. Now, I see what you're saying, Marty. You're saying that this is fatter than this, so therefore, if I could break down these with even more detail, you'd see it would pop out even more. But the idea is they're arguably symmetrically, unimodally bell-shaped. Now, they're squared off, which makes it a little bit hard to see. Why? Do you remember what the original distributions looked like? Remember what they looked like? The red one itself was bell-shaped. Yes, the red one already was. Here they are again. Here they are again. There's the red one, which is arguably bell-shaped. There's the orange one. The orange one has nothing to do whatsoever with a bell. It's this bimodal, weird, gappy. There's green to give you the bird distribution. It's symmetric, but it's not bell-shaped. There's yellow, not even close to bell-shaped, and there's blue, not even close to bell-shaped. So why would it be that these guys' bells would just show up once we start sampling? Question number 1. Oh, Veronica, answer number 1.
Because they're taking the average.
So what does, I love that answer. Let me go back, let's go back to one of the egregious, let's go back to yellow. You know what, blue? Not yellow, yellow's right there. Yellow. When you look at yellow, here's the yellow distribution, right? Where's the average of this distribution? 4.5, right? 4.5, that's the average of the distribution. Can you see on this curve right here where 4.5 is? On this curve. Where does it appear to be? Oh, David, say that again? The biggest one I heard in the middle? Yes, both of you are saying the same thing. When you treat this as a bell curve, it looks like the average is essentially in the highest bar, i.e. the middle of the curve. Did you see where the average was in the original distribution? It wasn't near the biggest bar. The biggest bar was to the left of where the average was. That's because it was skewed, right? Right? The average is right about here, 4.5. The highest point's over here. You see this 11 that's out here? Where's the 11 in this curve? Where's the 11? There are none.
It's an outlier.
What? So why didn't it show up in your sample?
Because you got to draw it 4 times in a row.
In order to get a sample average of 11, you'd have to roll it 4 times in a row. Nick, if it's an outlier, what's the definition of an outlier? Good. Give me a more general, I love that, Jolene, thank you. Give me a more general definition of an outlier. Something that is extreme. Oh, I like that. Somebody said something else? Out of the ordinary? Yes, extreme, unusual, out of the ordinary. If something is unusual, does it make sense we're going to roll it 4 times in a row? That's kind of the antithesis of an outlier, right? So what you've done by sampling a cohort at a time is you've given the outliers a chance to show their outlierness. When you have the actual distribution in front of you, you've got all 36 outcomes. But you're not talking about outliers. You're talking about, well, you can get an 11. This shows you that you don't get it very often. When you guys were rolling your yellow dice, did 11 ever show up? Did anybody get an 11 on the rolls? Of course. But you sure didn't get them 4 times in a row. You got an 11 and maybe a couple 4s, and the average ended up over here. But that's the idea, that those outliers should not occur 4 or 5 times in a row. Good. So, I love what you said, Veronica. When you're averaging, you're kind of finding the most common values. And the most common values can be wrapped up with one word. The what of the population. What's the most common value of the population? It ends up being the average, 4.5. Did you know? Let's put some of the other curves back. My red friends, undo. Red distribution. What was your average of your distribution? Let me see if I can guess. Right around 9? Was that your population's average, right around 9? Yes? Good? Okay, let me see if I can guess here. See if I can guess here. Blue, were you guys right around, I want to say maybe a little bit below 9, 8 point something? Were you in here, 8 point something for blue? Is that what you guys were? So, 8.6?
That's what I.
Or 8.16 or 17 or something like that. So you were in this bar? I'm going to guess by the biggest bar to see if I can figure it out. Yellow, we already nailed. Green, well, this is pretty obvious because you guys were perfectly symmetric, but it looks like it's right at 7, which I think you guys were. Good. Notice we got a bell. Remember what green looked like? It was the middle finger. But look, the ends fell off, right? The ends are gone. Although you could roll snake eyes, and you could roll a 12 in the population, it looks like it's very, very hard to average 12 or average snake eyes in a sample. And that's exactly right. How many different ways could you get snake eyes? Was it 2?
4.
4 out of 36. That's 1 in 9, right? There's a 1 in 9 chance of rolling snake eyes in that population. But in order to average snake eyes, you'd have to roll that 4 times in a row. That's like going to the store with Max and getting 4 roosters, isn't it?
No.
1 in 9 is just about 1 in 10. And getting 4 of them in a row will be like getting 4 roosters. It's not going to happen. Except for 1 in 10,000 trials, which is why you didn't see. Eventually, somebody sitting here will see snake eyes on average. It doesn't happen very often, hence because it's an outlier. Good, we regress to the mean. Very nice. And orange, here you guys are. It looks like you're. I'm going to guess your average is somewhere around 7. Somewhere around 7. Maybe 7.5. Somewhere around 7. What was orange's average? It ends up being 7. There it is. Oh, you know what? I should look. These bars are a little heavier than these bars. It probably is pulling more towards that side. Good. So even though in the original orange distribution, 7 was not the highest bar, in the sampling distribution, they are at every single, whoops, not delete, undo. Every single one of these distributions, these sampling distributions, every single one of them shows us the average of the population. Every single one shows us the average of the population. That's rad, because isn't that what we want to know? We want to know remember, we want to know how much more the kid with ADHD can concentrate if we up his dose to 30 milligrams from 15 milligrams. A lot of you are thinking, please, we'll do it right now. But the idea is you don't know what it is, but the sample is showing you what it is. Remember, there's a little bit of fiction going on here, right? I asked you a bunch of questions. Hey, yellow, what was your average of, what was your mu? What was your population? You're saying 4.5. You don't know that, right? You don't know that. You don't know what your population average is. So there's a little bit of fiction there. But you see what's happening is, we're seeing it on average. We're seeing it on average. Are we seeing it every time? Ooh, crap. See, there's a problem. There's a problem. Out here, what if your sample lied out here? Or maybe back over here on this side. Or you were in the red distribution and you were over here. David, go.
If your sample size, though, was like 8
Ooh.
instead of 4, wouldn't that like shrink them in even closer to the average?
Say that again, nice and loud. I'm gonna stop making these noises up here too.
If your sample size was bigger, wouldn't it like shrink your graphs even closer to the average?
Did you hear what oh. So did you hear what he just said?
Yeah.
So why does that make sense?
Because you'll get closer to the average
Why?
on average
Why?
when you have a bigger
Why?
population.
Why?
More time to roll.
Why? I mean, why does that why does that not increase variation? What David's claim is that it's decreasing variation instead of increasing it. Why wouldn't rolling it more increase the variation? Because you have more chances to roll the outliers, so to speak.
Right, but on average you're getting more. You're
Of
getting
the
more of the
average.
average.
Over
Plus
time.
May I? I think, Carly, go.
Because the probability of rolling the average or closer to the average is so much higher than rolling the outliers that over time you're going to keep getting closer.
I think you guys are saying the exact same thing. Remember the logic we had with the green curve? Why we don't get snake eyes? It's too hard to roll snake eyes 4 times in a row. It's even harder to roll it 8 times in a row. Exponentially harder, yeah?
Yeah.
So the question is, with a sample, this is only a sample of size 4. Nobody does samples on size 4. If you do, you lose your funding usually. But the idea is, yes, this is the sampling distribution. There's still some sampling variability in this, yes? So let's come back to that. Let's come back to that. I'm going to shut this down. And I created a little special Excel spreadsheet just based on the blue dice. This is not to, oh crap, it's right here. Not set up right. Let me shrink it down so you can see what's going on. You guys see that okay? Okay. I use the blue dice without loss of generality. What that means is the argument we're about to do, which is actually an argument tied to what David just said, will work for the blue dice, the orange dice, the red dice, the ADHD kids, the BP oil spill, the swine flu vaccine. Any study you want to do, we're about to talk about, will apply to that. It's exploring the idea of what sample sizes do to studies. It's exploring that. So I chose to use the blue dice as opposed to the other ones just because that was the first set that was sitting in front of me. So just realize that the argument we're about to look at here applies across the board. Okay, so first off, here is the distribution of the blue dice you guys came up with earlier. Now it's a little bit different here, and I have to keep doing this because the damn screen doesn't fit. It's a little too big. Now, this is loaded with random numbers. What I'm essentially doing right now is I'm rolling the dice just like you guys did, but I'm rolling them so many times that essentially I have the distribution in front of me. You can see how it's changing as I roll. That's just a function of the normal sampling error or sampling variation. But you see how this shape roughly looks? Who had blue dice before? There was 2 groups that had blue. This looks just like the histogram you guys had with an experimental error. Good. Now, I used Excel to replicate the study you guys just did. Check this out. This is the study you guys just did. The exact same thing you just did on your quiz when you collected all your data, except I've got about 1,000 trials where you guys had 50. You see the bell curve? Check it out. Check it out. Now notice how every once in a blue moon, these bars switch out who the tallest one is. But on average, which one is the tallest?
When you made the dice,
8, 8,8.5.
8,8.5. Hold that question, Di. Marty, remember your question about how is that red one a bell? Remember how I said if I split it down and make it more precise, you'd see it more? I split these in half. Instead of going 9 to 10, 10 to 11, 11 to 12, I cut it down to 9.5 to 10, 10.5. Does that make sense?
Yes.
And I had the luxury of doing that because I've got more samples and it actually fills itself out. So I didn't want to ignore your question, I wanted to answer it in time.
Okay.
Di, go ahead.
I was just wondering when you made the dice, what your plan was for which pips were going on which color.
That was that random Excel sheet I showed you earlier. Until I saw something that I liked, I'm like, I'll build that one.
Okay.
So,
That was right.
it definitely random, to a point. Then it kind of got my attention because I'm ADD. I'm sorry, I forgot to answer, you guys answered me. What bar on average is the tallest? The one that goes from 8 to 8.5, yes? Guess what? Isn't it in that bar? Remember the average of the blue, I think it was 8.2-ish, something like that?
Yeah.
So your average, most frequently drawn from samples, ends up in the bar where it needs to be. Now right now, it's clearly the tallest. But every once in a while you'll notice, it's not. There you go. That one's not the tallest. That one's not. That one, look at that one, it kind of squared off the top. But the idea is on average it is the tallest. But suppose you go draw a sample and you end up down here or you're this guy over here. Remember when we talked about outliers? You can get a sample that has an outlier value like this. Crap. So how do you avoid doing that? How do you avoid drawing an outlier sample or having that much noise in your sample? David, what was your solution?
Bigger sample
Get
size.
more data. Let's bump it up to a sample size of 9. Now, I want you to look at that bell curve right there. That's the sample size of 4 bell curve. Here's the sample size of 9. How is it related to the sample size of 4? How's it related?
It's also a bell curve.
Still a bell curve. How's it different?
You're
Less outliers.
shrinking.
Oh! Notice the 3, that 3 to 3.5 that was popping up every once in a while on the last curve. We're not seeing it anymore. It's too damn hard. Now hold it down. No, it won't dance unless I do this. You see what's going on, friends?
Yeah.
So we still get the bell curve, which is freaking awesome. That's cool. We haven't explained why yet. We just know that it is showing up. But we also knock the variability down. We knock the variability of the curve down. So it's more tight now, which means it's harder to get into the outliers. I still don't like it though, because remember the average is still basically in the highest bar or close to the highest bar. But what if we land out here? So how do we prevent ourselves from landing out there? More samples. Let's go to 16. David, you said 8. I apologize. I'm ignoring your 8 and going straight to 9. There's a method to my madness though. What do you notice about this curve? Even more bell-shaped. Now, does it look different than the one right before it? The previous one with the sample of size 9. It might be hard to see. Look at the probability. Did you catch how I changed the frequency to a probability? Such a bastard. Watch this axis. The highest point is now around 30%. So 30% of the time, you're landing really close to that average of 8 to 8.5, right? When you compare that to the original distributions, notice the highest was only at 16%. So when you increase the sample size to 16, on average, you're twice as likely, on average, to land near that average, if that makes sense. So once again, we're shrinking the curve in with a sample size of 16. I asked a question. See if you can catch this. Who's bigger, S or little sigma? S would be the sample standard deviation of this curve. Sigma is the standard deviation of the whole population that you calculated off the bat. Sigma's bigger, isn't it? Remember, sigma, if you remember from back here, is about 2.6, right? That's what you guys told me, 2.6, 2.7, somewhere in there. What do you think S is with this sample size of 16? If you had to give me an approximation for the value of S, what would you say it is right now? Approximate value. What are you doing right now, David? Explain it to me. What are you doing?
Going out to...
Hell yeah, you are! 2 standard deviations, right? Good. So you guys, stop me.
Wow.
See right here?
Yeah.
That's 7 up to about 9.5. 7 to 9.5 is, what's that, 2.5? That would be 2 standard deviations. Cut that into 4 equal pieces, correct? Up to.
1 1/4.
There you go. Oh no, cut that in half again, right?
Right.
So 1 1/4 cut in half again is 5/8, 0.6 something.
6.3.
0.63. Much smaller than sigma, isn't it? Much smaller than sigma. Good. And hopefully that makes sense. Shouldn't these curves be getting tighter? Per what Monica and Carly and David have all insinuated, these curves should be getting tighter as the sample sizes go up, because the outliers are getting harder and harder to get. If the outliers are getting harder and harder to get, that means averages should be getting easier and easier to get. So let's keep going. Let's go to a sample size of 25.
Crazy.
As the
Carly, go.
okay, as you add more, as your sample gets bigger and
Yes.
you add more data points, the probability of getting that average is going to get higher. Your data points are going to come in, so your standard deviation is going to get smaller.
That's what we're seeing, right? We're actually seeing that visually, which is so cool. I keep having a hard time centering this. I apologize. I do. Whoa.
Jesus.
Now it's at 35.
How's... We're at 25 now. I'm sampling 25. And if you can see behind, back here are the sums that are happening. So every time I press F9, it's rolling the blue dice, and it's counting those sums and average. Same thing you did, except now, imagine if I came in and said, oh, by the way, guys, you're going to roll 25 times, 25 times. 625, you're like, the hell out of your rule. And as well you should. That's why God invented Excel. That was the hand I thought.
Okay.
Please, Veronica, go!
But that was easy to find the 2 standard deviations because
Sure
of the
is.
number of bars. But if we were to have more bars, do we just eyeball it?
Yes, that's the best thing. If you need precision, you have Excel. But if you're talking about conversational estimation, I mean, go to the first one. Go back to a sample size of 4. right? Let's ballpark where two standard deviations. Here we go, you ready? Yeah, ish. Boom. How about that? Looks like it's from 5.5 to 10.5. That's what, 5? That's 5, yes? So, well, 5.5 to 10.5 is 5, right?
Yeah.
So that means 2 standard deviations covers 5 units. That means 1 standard deviation covers 2.5 units. Cut that in half to get the actual number of the standard deviation, which would be
1.75.
1.25? 1.25, 1.25. Does that make sense? So yeah, it's definitely a ballpark. Now if somebody says, no, I think it should go out to 5, not 5.5, you're not gonna be off by that much. If you're saying it's down here to all the way out there, then we gotta have a discussion about what 95% looks like.
Yeah.
Is that fair?
Yep.
Is it D? Good question. Thank you, sister. Let's go one more.
So
One more, please.
at what point do you decide
Hold
that
that thought.
the
That's a great question. I know where it's going, Carl. It's a fantastic question. Yeah. What is precise enough?
no, not exactly. Well,
Oh no, maybe not. I switch. Go ahead.
okay, so as your standard deviations get smaller, then your outliers get closer and closer.
Uh-huh.
So at what point do you decide, okay, this is like 1 unit away from the average?
Oh,
but
that
it
is
still-
the question I
it
thought you were
kinda
gonna ask.
doesn't- Okay.
Hold that, please hold that thought. It's a fantastic question. It's 244-ish bridgey question, which I love. Carly's saying, it's funny because on the way up here today, I thought of a 244 simulation that you run in Excel, which is how many trials do you have to run until you're close enough to notice a difference? It's related to your question. Hold that thought if you would. Now, this might, if you look at this might look exactly the opposite of what it should be at a sample size of 100, because here's what a sample size of 100 actually looks like. If you use the exact same x-axis that we've been using. Notice that right there?
But you switched it up.
Look, right, exactly. And for years and years and years I used this, to which Marnie asked, it's not a bell curve. It's not a bell curve at all. To which I then respond, okay, let me change the x-axis to that. Now notice, that's the exact same curve you were just looking at on the previous screen, but look at the units. 8.4 to 8.5, 8.5 to 8.6, 8.6 to 8.7. Fair enough? Ready? 2 standard deviations. Here we go. Whoa-ish. Okay, so I got 7.8 out to 8.8. That's 1, correct? That's 1. 2 standard deviations. 1 standard deviation is therefore a half, which means the standard deviation itself is around 1/4. Boom! So the S's are shrinking a lot, right? They're shrinking a lot as our sample sizes go up. We're out of time. I had a wrap up, I wanted to do with this, but you guys asked freaking awesome questions. Carly, can we pause your questions till Thursday? I've got a synopsis of all of these graphs in 1 page I want to look at with you guys, okay? Thank you guys, we'll see you, and Thursday will not be a very long day. I'm thinking 20 minutes you're out of here. Just to wrap all this up.
It sounds like fondue.
Fondue, 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 is that what you're chuckling about? I saw you chuckling, what did I say? I said fondue.
Yeah, fondue.
Next time I'll say Control Z.